Well, welcome back, everyone. Looks like we can get started today. So for today's class, we're finishing off chapter 17, handling one sample mean. Then we'll be moving into chapter 18, looking at how the methods are going to change for both the confidence interval and the hypothesis test when we consider two population means at the same time. The other bigger announcement is certainly that we're also getting closer to our second exam. Exam 2, if I could pull up the calculator or calendar here, is going to be on March 16th, the week right before spring break. So we'll get that out of the way before going on a much deserved vacation. This exam I'll be posting on Friday, the information, the exact coverage. I'm thinking it's probably going to cover chapters 14, 15, 17, and 18, but I'll know for sure once we get towards the end of our class where we end up on. After I post exam 2 information, the coverage, I'll do exactly as I did on exam 1, post the formula sheet, the page of notes that's going to be on the last page of the real exam, as well as 2 versions of sample exam 2 problems. Then when we come back on Monday, the 9th of March, I'll be sending out instructions first thing in the morning for scheduling your exam, just like we did on exam 1. Well, any questions at all, folks, about any of the announcements today, or any questions at all to start us out? Okay, well, let's finish off our chapter 17 and see how the methods change going into chapter 18. Once we get through chapter 18, after exam 2, more likely than not, we'll be turning over to handling categorical data for a little bit before going back into quantitative data. We're going to start getting more and more statistical procedures. So we'll also be spending time discussing when do you use one method, say chapter 18 versus a chapter 20 method, and when do you say use a hypothesis test or a confidence interval, and so on. So first, let's go back to about where we left off on chapter 17. We were discussing the formulas for doing the one sample t-test for a population mean. So if we're going to test the null hypothesis that the mean mu is mu naught against any one of these 3 different alternatives, we form the test statistic, very similar to chapter 14, except we have the population standard deviation S there, rather than, the samples standard deviation S there, rather than the population standard deviation sigma in chapter 14. The computation of the p-values is not too bad. It's just about exactly the same as in chapter 14, except we put t in that position instead of norm, and we also have to input the degrees of freedom, which is just the sample size minus 1. We looked into 3 different scenarios in example 5, parts A, B, and C. We're just looking across these 3 different tests, how to get the p-value out. So the next thing we're going to do is look at a problem that actually has context, analyze it top to bottom, and give a strong conclusion. But any questions on the refresher, on the method itself? Okay, well, here's our first problem for the day to start us out. And it's kind of a fun problem to come back to because we've been looking at this in pieces ever since the first day of class, where the major question was, what is the population? What are the parameters? What are the statistics? But now we're going to be able to finally get to a position where we can analyze these data completely. But let's refresh on what's going on in the context. We're looking into the ankle brachial index. We'll abbreviate that as just ABI in this problem. It compares the blood pressure of your arm to the blood pressure of the leg, and it's an indicator of different diseases, including some arterial diseases. This looks important. We're told a healthy ABI is 0.9 or greater, and that's going to give us a value. Oh, forgot to set up my pens. Give me a moment. This has to be done every single time I log into the workstation, but apparently today I forgot. This workstation, all the settings completely reset every single login. Oh, I think I like that one as an orange pen. Just a couple more highlighters and we'll get started officially. Okay, back to what we were looking at over here. When it says a healthy ABI is 0.9 or greater, what that's giving us is the hypothesized value, the mu naught that you see in the formulas. So mu naught is going to be 0.9 coming from this part here. Now we take a look into the context of what the study itself is about. The study said the researchers obtained the ABI of 187 women with peripheral arterial disease. So that's given us a sample size N to work with. N equals 187. We have a sample mean of 0.64, so that's one statistic. We know that's a sample mean because it says here the results, meaning the results from pulling the sample gave them that mean. So definitely not the population mean. We have X bar at 0.64, and there's a standard deviation of 0.15. So there's our sample standard deviation S, a value 0.15. We're going to analyze these data at the 1% significance level being indicated here. So from that statement, kind of running out of colors, but let's go with this color. Significance level alpha will be set to 0.01. And it's a question, so this is essentially our alternative hypothesis. When we go to set up our hypotheses, we're being asked, at that 1% significance level, do the data provide significant statistical evidence to conclude that, on average, women with peripheral arterial disease have an unhealthy ABI? So this entire statement right here, that's essentially the alternative hypothesis, HA. We must write it in terms of the parameter and in terms of the hypothesized value, the 0.9 as well. But this gets us started, just analyzing the context. Next thing we'll do is say what the parameter is in part A, state the null and alternative, and then from part C down, it just turns into a math problem, working the formulas that we stated. Any questions at all, folks, to this stage? Okay, well, going back to this part right here, here's our unknown parameter. We can say mu is, I'll go with true mean, or you could say population average, any kind of combination of those words that conveys an average or mean and that conveys a population will be just fine. I'll say mu equals the true mean. You have to say mean of what quantity specifically, but the statistics saying it was a mean ABI of 0.64 tells us the unit. It's a complicated one. Remember, it's blood pressure comparing your upper arm to your lower leg, but let's go with ABI. True mean ABI for short. For all, when we say for all, we're trying to indicate the population now. But what we know for sure is the sample of 187 individuals comes from the population. So when they describe the sample here, we just turn the 187 into for all. We have the population. We'll just say for all women with peripheral arterial disease. So with that parameter down, notice we're only describing mu because we're just doing a confidence interval on mu. We're just doing a hypothesis test on mu. So we don't have to describe sigma. It wouldn't be any harm if you did, but it's more appropriate to just land on mu and move on to the next part. From here, we're ready to state the null and alternative. And here's pretty much what the structure looks like. We'll leave some blanks and we'll fill it in. We're going to test a null hypothesis. Mu, our author always puts equality here, like we discussed before. If it's appropriate to put a greater than or equals or less than or equals, say like you might do in a biometry lab, that's completely fine as well. I'll go with the author's approach and just put the equality in the null hypothesis. We're going to test that null and fill it in a moment against an alternative, HA, go mu. I definitely don't want to put equality here. There can never be an equality. It's either not equals, less than, or greater than, but we'll cross that bridge when we get there. Let's put in a blank and say at. Here we're indicating the level of evidence that we're required before we reject the null and conclude we have evidence for the alternative. But that's what the significance level alpha is all about. So we'll say at alpha equals 0.01. So we'll have evidence for this alternative when it's completely filled in if our p-value is below that level, strictly below it. Putting all that down on paper, here's where this value comes into play. We're testing against this, the 0.9. So put in a 0.9 here, 0.9 here, a little bit of space between, and then just reread this sentence. It says, do the data provide significant statistical evidence to conclude that, on average, women with peripheral arterial disease have an unhealthy ABI? We can use the information above where it says healthy is at 0.9 or greater. So you might have went greater than or equals to 0.9 in this null, which would have been fine. But that means having an unhealthy ABI means we're going to use a less than symbol for a left-tailed test. So less than will go right here in our alternative. So we're done with those parts. This is sometimes the hardest part about statistics itself, just saying what the parameter is and saying what the hypotheses are. Any questions or comments at all, folks, getting this down on paper? Okay, again, from here on out, it's like a math problem at this stage. We have some formulas that are going to tell us exactly what each of these quantities represent. So if you see the word degrees of freedom, we wrote this in as DF to stand for degrees of freedom, great shorthand. It becomes a formula if we write in n minus 1, which means we're just taking 187 minus 1 or a 186. If you just put down 186, that would have been fine as well. Another formula is the standard error. This one's a little bit more involved, so let's take our time with this one. When you see standard error, it's context sensitive. There's different standard errors in chapters 18, 19, 20, and so on. But in chapter 17, when we're testing just one mean x mu, we're talking about the standard error of x bar. So we write this as SE of x bar. Let me try to fix the penmanship on that. I want that bar to really show up. Okay, third try is the charm. Standard error of x bar. The formula for this is you just take the sample standard deviation S, divide by the square root of the sample size n. So that's the whole formula on paper. Now we're plugging our values, put in 0.15 to start, divide by square root of 187 for the sample mean n, and then just grab a trusty calculator. Don't forget to bring yours in the exam room. A basic scientific calculator will do just fine. Graphing calculators aren't allowed, but also make sure to bring your own. The testing center could potentially run out. They have a couple loaner calculators, but they don't have a lot. So in the calculator, this is going to be 0.15 divide by square root 187, and that's our standard error. It says to round to 4 decimal places, and that's pretty standard for this standard error. So let's put it in as 0.0110. Let me double check the rounding on that. Rounding with carry always just seems to make me a bit uncomfortable. So that's the 5th decimal place, 1, 2, 3, 4. Yeah, that looks about right for the rounding. So now that we've got the standard error, we move on to just the next formula, the test statistic T. Any questions on either of these values so far? Okay, so for the test statistic, what we're now putting together is this formula. It goes T equals, take the sample mean x bar, subtract from that the hypothesized mean, mu naught, which is the same value you have down here in both your null and your alternative, divide by the standard error of x bar that we just calculated, It's a fast computation, so let's put in place of X bar, making 3 substitutions, 0.64 for the first substitution, subtract from the null hypothesis, our hypothesized mean, 0.9, divide by the standard error we just calculated, 0.0110, and we're about to get a value out. So another calculator quick operation, this will be 0.64 minus 0.9. You know, that doesn't look like it's a big difference really, until you look into the approximated standard deviation. That standard error is very, very minuscule because the sample size was pretty large in the study. So when we divide by that, we get 0.0110, negative 23.6364. That is, in terms of magnitude, a gigantic test statistic. This tells us we are absolutely, assuredly going to reject the null in favor of the alternative. We'll still calculate the p-value, but it's going to be given in scientific notation because it's going to be so minusculely small. And another thought about this is the interpretation of this test statistic is exactly the same as what we did in chapter 14. Let's put it down on paper just for the review on that concept. That number, negative 23.6364, tells us that the distance from the sample data mean X bar, so the data that we actually got, the distance from that to the hypothesized mean of the entire population. So the distance from the mean X bar to the hypothesized mean mu naught equals 0.9 is, well, I can't say exactly standard deviations because it's a standard error, but it approximates the standard deviation and it does a pretty decent job. So we can say is approximately 23.6364 standard deviations away. Here, I just focused on the magnitude. That's how far they are from each other. The negative sign just says the sample mean is to the left of the hypothesized mean. That distance is gigantic once again, so it tells us this assumption in the null hypothesis is totally unreasonable. Even if this was, say, -4 standard deviations approximately, that's a very large distance as well. So that's all this really is trying to compute. It's a type of z-score, except we call it t, because when we compute the p-value, we're using the t-distribution instead of the standard normal one. Well, again, these are the concepts we were talking about in our chapter 14. That's the kind of nice thing about chapter 17 is it just reviews and reinforces what we did in that prior chapter. Next thing we'll compute is the p-value, and here's how it goes. We have to be mindful of the direction we're going. So see the notes above, as well as the example with the 3 different parts for the left tail, right tail, and 2-tail test. For the left tail p-value, this one's going to be p-value equals, I'll write this in syntax that we would use in RStudio. It'll be probability t-distribution. Throw in first the test statistic t, negative 23.6364. So t comes in here from part E. Then in the next position, you put in the degrees of freedom, 186, that came from part C. And because it's a left tail test, we just stop right there. We don't have to say lower.tail is false. We don't have to take the absolute value of something. We don't have to double it. And this is just the degrees of freedom part right here. If this was a real exam question, I would have to just give you the p-value and you would skip down to part G, giving the interpretation. But let's compute this. Probability t-distribution, negative 23.6364 for the test statistic, 186 degrees of freedom gives us this number. I'll just convey, say, how about 3.153 for significant digits. E right here is really just saying times 10 to the power negative 58. So E for exponent on base 10. So negative 3.153, excuse me, positive 3.153 times 10 to the power, and I forgot that order of magnitude, negative 58. It's almost at the level where this calculator is just going to give up on scientific notation and say zero. It's never truly zero, but eventually it's a finite machine. It runs out of the size of magnitude it can provide you. So negative 58 goes here. Now we've got our p-value, but that is very, very small. If we go back to our significance level alpha right over here, this is absolutely less than 0.01, which is equal to alpha, so we will reject H naught. Always put this down on paper every time we do a p-value because it leads into part G. But if this was a homework problem, I'll just emphasize here in the box, that's the number that's expected. Give the number the scientific notation. If the calculator just gives you a zero at that point, just say approximately zero would be appropriate. Now, for rejecting the null hypothesis, we're ready to give the practical conclusion of the study. It means we have significant statistical evidence that the alternative, right where the red dot is true. We just have to say what it means in ordinary terms, using no specialized statistical jargon. But just like we've done before in all the prior problems, we're just going to read this left to right, but say what mu was in part A. If we made a mistake here in part A, you won't lose points again in part G. Just say what you said mu was in the initial portion, part A, and you'll be just fine. So here's how I would word this. For p-value that small, you might use special words and say, there is overwhelming significant statistical evidence I like to mention the significance level when I say that, kind of like saying what the confidence level is in a confidence interval analysis. I'll say at the 1% significance level, the author of our book doesn't do this, curiously. So if you left that out, you wouldn't lose points. But again, it's kind of weird. We're very, very adamant that we put in the confidence level, but somehow the author doesn't decide that this is just as important. In my view, it kind of is. So I'll get in that habit personally, but I'll leave it up to you on how you decide to write out that part. So overwhelmingly significant statistical evidence at that significance level, that now we just jump up here and read this out left to right, starting with mu, that the red dot wouldn't hold still. Here we go. The true mean ABI for all women with peripheral arterial disease so that's the mu part, and I'll just say is less than 0.9. And that ends the whole sentence. So we have to directly interpret whatever our alternative hypothesis happened to have been. And there's further things you want to say. You could add a little bit more to that. You could say in ordinary words, this shows that women who suffer from this condition have an unhealthy ABI. So let's put that down just as an extra statement. This shows women with this condition, by this condition we mean the peripheral arterial disease, have an unhealthy ABI. And the sentence isn't over, but we were saying unhealthy ABI because it's less than 0.9. And the original context says healthy is at 0.9 or higher. But the sentence is still not done because it seems like we're making a statement about every single person who has this peripheral arterial disease. And there's going to be plenty of people that actually have a healthy ABI. So this statement as it stands on paper right now is false until we say on average. Because don't forget, the whole problem was about the mean mu in the very first place. So we have to say that somewhere if we're writing down this statement. The statement below is optional. You absolutely have to say this part. So let's emphasize this, just like we said with the confidence intervals. Be sure to directly interpret the hypothesis test, meaning whatever you said the null and the alternative hypothesis was right here, we have to come back here, involve whatever you said the parameter mu was in your overall conclusion. So when it says provide a practical conclusion, we mean this part right here. Anything additional you want to say, that's going to be up to you. Well, we did it, folks. That's the conclusion of chapter 17, filling in all the logical holes that we had in chapter 14, and there was quite a lot. This is our first bona fide statistical method that is widely applicable. And all we're doing now is just extending this into other situations. If we're looking into two independent populations instead of one, is what chapter 18 is all about. But congratulations on getting through this chapter. Any questions at all, folks, before we turn to the next one? Okay, well, let's take a look into, after getting through chapter 17, what chapter 18 is all about. Okay, starts off with a nice, interesting theorem coming out of probability theory out of nowhere. But I want to just give you kind of a lay of the land of what we're doing in these problems, what the formulas look like. So as we scroll through the notes, the stuff we're going to fill in, here's the entire set of two sample t procedures. We're estimating the difference between two means. And so our confidence interval has this form. We're going to compute the difference between sample means. We'll have a different standard error, but another t-star, just like before. Standard error formula gets kind of weird, so we're going to take some time just to discuss how did that formula pop out of nowhere. If we're doing a test statistic, it'll have this form, just a difference of means. This is because we're assuming the null hypothesis will be this in the entirety of chapter 18. The difference between the means is 0 is our null. That's why it's just the difference between the sample means and the numerator there. The degrees of freedom formula becomes involved, so we'll say some words about that when we get there. Then we'll do like we did in the other notes. We're going to run through a confidence interval procedure in the study right here. We'll turn it over, look at carefully conditions for the two sample t procedures, and then run through a hypothesis test, this time using raw data, so we'll show how RStudio goes for a problem like this one. So really, it's going to feel a lot like we're doing chapter 17 again, but the context has slightly changed. There are now two independent populations, which means we have two random samples, two sets of sample means, and just slightly different formulas. So here's where it's all going to start. This theorem right here, its purpose is to give us a standard error. And I noticed when I was proofreading this problem, this should not have been here. That's kind of a confusing sentence. Let me strike it through. I meant to delete that. I reformatted this problem, but it looks like I just didn't delete that. I put that statement pretty much down here in different wording. So sorry for that. Strike that through. Just kind of run it, ignore that statement, and then example one is going to make more sense. But let's start on the probability theorem. It says Assume x and y are two independent random variables. Keep in mind, when we say random variables, a sample mean like x bar 1 is such a variable. So sample means, statistics themselves fit into this. When we say independent, what we mean is when we take the sample and make measurements from one sample to the next, the measurements we made in one sample have no influence on the second sample whatsoever. So we'll denote the mean of x by mu x with a subscript, the mean of y by mu sub y. And then we have three different formulas. Oh, first, don't forget the standard deviation, or rather the variance of x and y are going to be denoted like these. It's been a while since we've talked about standard deviations and variances, so let's just put something on paper first. If s squared is the variance, then s, which is directly square root of s squared, is the standard deviation. And that's coming all the way back from the chapter 2 notes. We're at midterm, so that feels like quite a while ago. We defined the variance, but we mentioned we're primarily using the standard deviation. This is one of those weird times where we really need to use the variance to run through the formulas. So we know we're dealing with the variance if there's a power 2. So variance for variable x is sigma squared, and sigma squared sub y for variable y. Now finally, here's how the formulas go. If we add or subtract the random variables, much like adding or subtracting two different sample means down below, all we're doing is adding or subtracting the means of both of those variables. As far as variance goes, it doesn't matter if you add or subtract them. Variance always adds together, and that's a really interesting fact from probability theory. In the standard deviation, once you have this variance, following this process below, you just take a square root. So go from here to here, take the square root, and now you have the standard deviation. So that's how the theorem works. But we're going to work it into this problem. We're going to say, gather two independent simple random samples of sizes n1 and n2. This will come from two populations distributed normally, but the central limit theorem can weaken that assumption if the sample sizes are large enough. We'll say, by the central limit theorem, we can write this down. The sample mean x bar 1 is distributed in this way. I'll have mu1 for its mean, sigma 1 divided by the square root of n1, sample size from the first population, for its standard deviation. So that's its mean here. And that's the standard deviation here. Likewise, this is also a standard deviation for the second variable, x2, has a mean mu2 and standard deviation, sigma 2 divided by the square root of n2. Lots of subscripts. That's one of the major challenges already when we're dealing with two independent samples. So what we'll do here is find the approximate sampling distribution for the difference in sample means. And the moment we do that, this is what we're really producing. This will be the central limit theorem for x bar 1 minus x bar 2. And that's where all of our statistical procedures really start. If you can get a central limit theorem down, you can provide a standard error. You're probably going to use a fancy distribution like a t-distribution, but we start really right here. So here's what we can do first. We want the mean, so we can say the mean of x bar 1 minus x bar 2 is, following the probability theorem, it just says we're using the minus. So read this out, only looking at the minus sign. That's what this formula is saying now. We take the mean from the first variable. Here it is, mu1, and then subtract the mean from the second variable, mu y. That'd be this mu2 right here. So we can say it's just simply mu1 minus mu2. So when we go to write out our central limit theorem, we'll say x bar 1 minus x bar 2 is distributed normally, and this quantity here is what's going to go in the first position, much like in the statements right above. Now we need the standard deviation, but we have to go on an interesting jaunt. We need the variance first, then we can take the square root of those and get the standard deviations. So let's work this out in stages next. That's a standard deviation. So if we want to go up to the variance, we have to take an equation like this, square both sides, then you get s squared. So let's say the variance of x bar 1 is, go here and just square exactly what you see. If you square that, you're going to get sigma 1 squared over n1. Square root falls off, and you have a power 2 on your sigma now. And same process for x bar 2. And the variance for x bar 2, the second sample mean, is same thing, just change the subscripts. That's the standard deviation, so squaring it gives the variance. We'll get sigma 2 squared divided by n2, like before, without the square root. So now we have two different variances, and this theorem is telling us if you have two different variances, but you're either adding or subtracting those variables, we're subtracting them, you're going to add up the variances. Variances never get smaller, they expand no matter what operation you do on them. So down below we can say the variance of, this is really all about the difference in means. That highlighting looks funny, so I'll take that off. Let's go x bar 1 minus x bar 2 is, just take these two things that we computed. It'll be sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. So a lot of work on getting our standard deviation. It started with just citing the central limit theorems for the sampling distributions of x bar 1, x bar 2. We squared them to get the variance for both random variables, x bar 1, x bar 2. Then the formula just said, add them together. So this is the add them together process right here. Final thing we do to get the standard deviation is following this process. If you have a variance, square root it, and now it's finally the standard deviation. So slap a square root on that. We'll call it a standard deviation next. The standard deviation of the difference in means, x bar 1 minus x bar 2, is, we're going to have to scroll on this to fit it in, square root of sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. So that's where this formula finally comes from. When it says find the approximate sampling distribution for the difference in sample means, we have all the parts we need. We needed the center, the mean, mu1 minus mu2, but you also wanted the standard deviation, the variability in it, and it's this entire structure. So we have one big conclusion now. We can say, therefore, we take two independent simple random samples, calculate an x bar 1, and we calculate an x bar 2, but then we do another operation and subtract them. The probability theorem above is going to tell us now that this will be distributed still normally. That's another big probability theorem as well, that's still a normal distribution when we combine normally distributed random variables. What the probability theorem above told us is the center for this normal distribution is now mu1 minus mu2. That's just the difference in the population means. And that's what we would expect. It'd be really weird if that came out as something different. If the x bar 1 is approximately mu1 and x bar 2 is approximating mu2, then subtract them. It should be approximation for the difference in population means, mu1 minus mu2. For me, that part just seems about right. And this is the part that's weird. Here's the standard deviation. Because of the way probability theory works with variances going into a standard deviation, this part feels like it comes out of thin air. So that's why we took some time discussing it. The standard deviation for the difference of means is sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. So that's the random portion right there. Well, any questions at all, folks, on getting to this derivation? Okay, we kind of already said what it is already here, but let's make it look more official. This is the central typically we capitalize that, make it feel more important. The central limit theorem for x bar 1 minus x bar 2. Well, we did it, folks. Now that we have a central limit theorem, we essentially can restart everything that we did in chapter 17. First thing we want is a confidence interval. We'll admit that we don't know mu1 and we don't know mu2, but just like we did in chapter 17, we further are being honest, and it's very rare we know sigma 1 or sigma 2, even rarer for us to know both sigma 1 and sigma 2. We're going to just say those are absolutely unknowns as well. If those are unknowns, what we need next is a good standard error. So that's what we're going to compute very next, down below. So example 2 is in the same setting as this entire chapter. We have two independent, simple random samples. We have to be careful that they're independent. For example, if we're taking polling data where someone measures a response between 0, totally against, and maybe 10, completely in favor of some measure, and we're, say, polling people from different counties in Idaho, these people should never, ever be in the same room when we go to record the responses because they can influence one another. So that's one way we're thinking about independent. One sample's observations can in no way influence or affect another sample's observations. Once we have those two independent simple random samples with unknown means, unknown standard deviations, we can compute the standard error of the difference of means. It's denoted by SE, just like before, of x bar 1 minus x bar 2 by writing out this. First, notice that we can make this set of computations here, or approximations rather. Sigma 1, it's an unknown quantity, but it's approximately equal to the sample standard deviation S1. So we have unknown on the left, but that's just the statistic coming from the data. We'll have that value on the right. And likewise, from the second population, sigma 2 is unknown, but it's approximately equal to its statistic, S2. And that's effectively all we're doing. We're going to where those two parameters are, the unknowns, and plugging in another approximation into the problem. And this is already an approximation in and of itself to give us a standard error. So the standard error of x bar 1 minus x bar 2 is going to be equal to the square root of, we're following this structure here, but just throwing in the statistics. So we write this as S1 squared divided by sample size N1, then plus S2 squared divided by sample size N2. And that's our entire standard error. From there, we're ready to state a confidence interval. A confidence interval would look like this. A level C% confidence interval, I'll just write CI for short on confidence interval, will be of the form, take x bar 1 minus x bar 2, because that approximates mu1 minus mu2, just the difference in sample means. We add and subtract a critical number, t star, and then we multiply it by a standard error, SE x bar 1 minus x bar 2. And that's just our new formula for the standard error. So this part right here plugs into that part there. So far, it looks pretty much exactly like what we did in chapter 17, but there's one small change. That t star, we'll compute it using the t distribution just like before, but it actually has a very, very complicated degree of freedom. There's one thing that's going on in these notes that our author only really discusses towards the very end of chapter 18. We are making no assumption whatsoever about sigma 1 and sigma 2. There are certain tests that can use a pooled standard deviations together and give you a really easy degrees of freedom. It'll be sample size 1 plus sample size 2, subtract 2, and you're done. But our degrees of freedom are going to get really complicated because we're not only saying sigma 1, sigma 2 are unknown. Let's just say it right here. We also do not know that they're equal. We're not going to make that assumption either. We'll say here, therefore, we will not even assume sigma 1 is equal to sigma 2. So we have a very, very broad procedure that we're using. It's extremely applicable. And even if the assumption that sigma 1 is equal to sigma 2 looks reasonable, this is probably still the better test. When we say 95% confidence interval, in fact, 95% of the samples are likely to capture the true parameter. More often than not, if we pull the variances together and use a pooled t-test for two independent samples, when we say 95% confidence, more likely than not, we're overstating the confidence. When we give our p-value, usually it's smaller than it really should have been. There's a whole other statistical test to see if this is even a plausible thing to do. But with another statistical test, that just gives you another chance for type 1 error, type 2 error. You have to do more and more estimates. And this can turn into an infinite regress of maybe you want to test if the means mu1 and mu2 are equal. Do another test if sigma 1, sigma 2 is equal. But then you have to verify if everything went well on that test. You can see how this is just essentially spinning your wheels. So people found a way around this, and this is the procedure we're going to state down below. With no assumptions made about sigma 1, sigma 2 at all, we're just saying now we're approximating twice. Here's what happens to the degrees of freedom. It turns into an absolute mess, but I have some words here. This is an estimate from the gentleman Satterthwaite. Do not know how to spell that. Satterthwaite, or pronounce it apparently. Approximation for the degrees of freedom. So this right here is not making any one assumption whatsoever about sigma 1 or sigma 2. They're fully unknown. If we really mean that, we're also not assuming they're equal to each other either. This is going to be a confidence interval for the assumption of unequal variances. This will be a test statistic for unequal variances. Notice it's nothing too fancy so far. That's the difference in the sample means, just a different formula for the standard error, the one we derived above in the notes. The test statistic is just the difference in the sample means again, divided by the standard deviation. But that's the weird part right there. The degrees of freedom turns into a big formula. It gets smaller and smaller and smaller the more unequal the population variances become. The closer the population variances become to equal, the closer this is just going to turn into sample size N1 plus sample size N2, subtract 2. But again, if we're not making any assumptions, if we drop the degrees of freedom a little bit lower by using this, taking any evidence whatsoever of finding unequal variances through S1 and S2, this will make the degrees of freedom smaller, but that will have the effect of making the confidence interval wider. And that's good because now we'll be honest when we say 95% right here. We'll make our test statistic a little bit bigger, our p-value is a little bit bigger, but that's good too because that'll minimize a type 1 error. Our p-values are going to be more accurate and our confidence intervals widths will be more reflective of the real margin of error we're trying to get into. So this is our whole entire method. We're going to work through it carefully, in particular working through this formula here. On the left is the formula that's given in the textbook. But if you look at these things really carefully, S1 squared divided by N1 plus S2 squared divided by N2, that's just the standard error risen to power 4. So this is the way I would calculate it. It's a small shorthand, but anything you could do to make this formula a little bit shorter is well worth it. We'll often know that quantity already, raise it to power 4. So really the whole interval or the whole formula is just showing how the denominator goes using a known value from a prior computation. We're told it is an approximation. It'll be accurate if the sample sizes are 5 or larger. So the whole method falls apart if you have one sample at size 4 or 3, something like that. You have to be at least at sample size 5 to use this in the first place. If we're not there, well, we've got problems. Maybe we should have designed the test better to ensure sample sizes were 5 or larger. But things go wrong. Sometimes the whole test, the whole research goes sour. Maybe this is animal testing and too many of the lab mice died and we were below 5 on one sample. That's a tragedy. We have to do something else in that case. Well, any questions or comments at all, folks? Just looking at the formulas, the one we derived and the new ones down below. Okay, so this is the entire confidence interval procedure. Below is the hypothesis test. And once again, notice the null hypothesis is mu1 minus mu2 is 0. This is our standard null hypothesis for the entirety of chapter 18. We're assuming that there is no difference between the populations, that the difference in the parameters are 0. So this is the null for all of chapter 18. Then we have 3 different alternative hypotheses: the two-tailed test, right-tailed test, and left-tailed test. And notice this structure that we wrote down for the syntax in R and getting those p-values, exactly the same as what we wrote down in chapter 17. The only thing that's actually different is when you say df right here, it came from this formula. So that's the real change. So no actual change in what we write down, just a change in computing the degrees of freedom. Well, with all this down on paper, we're going to work on the hypothesis test first, then turn around and show how the two-sample t-test will go right after. Just to mix up what we did in chapter 17. In chapter 17, we had the raw data for the confidence interval, and we had just summarized data for the hypothesis test. So I flipped it around on these notes so we can get practice doing a confidence interval with raw data, and then, a confidence interval with summarized data. Then we'll do our hypothesis test down below with the actual raw data. So we'll show how this works in RStudio for data like these. Well, before we get to that, here's how example 3 is going to go. This is a pharmacological study, and it was published a while ago, admittedly, 1984, in a toxicology journal. So this one was a major study concerning public health. We're told in this pharmacological study, researchers measured the concentration of the brain chemical dopamine in 6 rats exposed to the chemical toluene I hope I'm pronouncing that right, and 6 control rats. And toluene is used in lots of different applications. It's kind of everywhere. It could be in, say, spray paint cans. It could be in nail polish remover. It could be in hobbyists' rapid dry. I'm losing my words on this. It could be in some kind of like super glue that hobbyists might use to put models together. It's used in a lot of different things. And back in the day, probably currently as well, it was massively abused. People would inhale this to try to get a fast high. And so people want to study exactly how does this work to try to take on this public health problem. It says the summary statistics for concentration of dopamine, nanograms of dopamine per gram of brain matter, apparently, in the striatum region of the brain, are provided below. So this was a designed and controlled experiment. That means when we give a conclusion on this one, we can now use language of cause and effect because of the controlled experiment on this. There were 6 rats exposed to the treatment, toluene exposure, and 6 rats exposed to the control, just a normal happy rat in an environment given food and water, just like the other one, but no toluene exposure in the control. They had 12 rats altogether, and they randomly assigned the rats to either the treatment group, toluene, or the control group. And so that tells us this is an experimental design. And so we can use cause, effect, and effect language when we go to write our conclusion in this problem. The question was, is there evidence that toluene causes an increase in dopamine levels in rats? And this can be analyzed 2 different ways, really. It could be a hypothesis test, but for this problem, we'll study the confidence interval when we give our analysis. The confidence interval is nice because it's going to address this question right here, but also provide the estimate for the difference in population means, mu1 and mu2. Well, here's our data table giving us everything we have. But notice it's also kind of tricky because there's the toluene group, the control group. There's one sample mean, another sample standard deviation, and then another sample mean, another sample standard deviation. So if it's helpful, it's not a bad idea to just write down in the margin what these statistics are in your own wording. So I'll put here for toluene, let's use colors to just to say which population we're talking about. So for population 1, the experimental treatment group, toluene, we had a sample mean here. I'll call this just X bar 1 generically, 257, 8.0 nanograms per gram. I'm going to use that same way they wrote the unit. So that's nanograms of dopamine per gram of brain in the striatum region. Kind of morbid when you think about that. And the sample mean S1 is 411.84 nanograms per gram. The other thing we're going to need is the sample size, N1. We're told 6 rats. None of them died over the course of this experiment, so we have all 6. Then for the control group, let's write this out as well. In the control, we have a sample mean in row 1. X bar 2 is 1880.4. S2, 411.84. And now that I've written that, I notice I have a typo here. The standard deviation for toluene is 565.19. Definitely the sample's standard deviations are different, and probably the population standard deviations are different as well. So again, we're not making any assumption about sigma 1, sigma 2 being equal. This is going to be the unequal variance procedure in our confidence interval. Last thing, just to finish this off, sample N2 is 6 rats as well. So even though this is kind of tedious to just write out all this information again, we're going to drop informations into those formulas we saw above that do get involved. It's a good idea to organize so we don't accidentally flip one thing to another like I did on this S1 here after the correction. Next thing we need to do is, just like we've done in chapters 14 and 17, we're going to give a conference interval. We need to say right here now, before we even get started, what are we estimating in the very first place? That's the unknown, now plural, parameters. They're both means. It's going to be mu1 and mu2. Now here's how I would word this. Instead of writing out 2 sentences that could get kind of long, you can combine this together in this sort of way. Let mu1 and mu2 denote, instead of saying dopamine in the striatum region of the brain, I'll abbreviate it a little bit to say denote the dopamine. Let me start over. Denote the mean. Don't forget, this is about averages or means. Denote the mean dopamine concentration for rats. We need to mention the population of lab rats that could be in this group. So I'll say briefly, rats exposed to toluene. So we mean all lab rats of this grade, this certain type that they use in the experiment, opposed to the same exact conditions, the same cage, the same level of toluene. We're saying that this is going to be their average dopamine concentration in the brain, but I've just abbreviated here. Then go and, because we're mentioning 2 means at once, go to the second population, mu2. We'll say here, and rats in the control group, which means rats being very well taken care of for. They'll have a nice cage, water, food, and definitely no toluene leaking into that cage. We need one more word. I'll put here, respectively. That's one of my favorite words in the English language, because when you say mu1 and mu2, and then you say exposed to toluene and rats in the control group, respectively, what you're really doing is you're setting up a mathematical 1-on-1 correspondence so that now this sentence is saying mu1 goes with this exposure to toluene and mu2 goes with this rats in the control group. That just cuts down the writing by almost half. So it's a great way to write down, if you have to put down 2 parameters or even 5, like we might in, say, chapters 21, this is a great way to say it. Well, any questions at all, folks? Putting the parameters down on paper? Okay, at this point, it's a math problem. We have formulas we're ready to run with. We want first the standard error for the difference in sample means. So this entire wording right here is saying compute SE for x bar 1 minus x bar 2. Forgot the subscript on one of them. There we go. So that's what we mean by standard error for the difference of sample mean 1, sample mean 2. Then this is just one gigantic square root. I mean, it's not that big, but here it is. The formula says take this, S1 squared. This is the formula that we derived. Divide by N1, add to it S2 squared. Divide by N2. So let's plug all that in. On paper, here's what it would look like, and even bigger square root looks like. For S1 squared, we're squaring that, 565.19. Power 2, divide by sample size 1, which is just 6. Then go plus 6 in this denominator. S2 squared is taking the 411.84, squaring it. And again, we've mentioned this quite a lot, just for hints on doing exams. If this was an exam 2 problem, and this is on paper, let's say it's a 5-point problem, even if you make a mistake on the calculator, you're probably getting 4.5 points out of the 5. So this is a gargantuan amount of partial credit. Get in the habit of putting the formula down, that's partial credit as well. You're indicating to me you know which formula fits. And this is essentially all of the credit on the problem. So that's an insurance on just making a simple mistake, putting this inside a calculator, because it is a lot to calculate now, even with a calculator like this one here, or a basic scientific calculator. So here's how I would type it in RStudio, which is similar to what it would look like in a scientific calculator. SQRT, your calculator might print out a square root symbol. 565.19 power 2. Then when I go to divide by 6, I'm not dividing the exponent. The calculator is going to follow order operations, square first, then division by 6. Then go plus, do it all over again with the second standard deviation. 411.84 squared, divide by 6. That's finding our standard error. I'll keep all the decimal points it gave us. 285.4972. So that is the approximate standard deviation for x bar 1 minus x bar 2's sampling distribution. It's really large. So our confidence interval is probably going to be really wide as well, thanks to that standard error. We can't quite get to T star just yet. The degrees of freedom is not 6 plus 6 minus 2. It's not 10 whatsoever. Notice the sample standard deviations, they're quite a bit unequal. So my bet is you would get a degrees of freedom of 10 if they were exactly equal. With them being a little bit off, it's going to drop down to maybe 9 or 8. If this was, say, 100 and that's 500, it's going to drop even lower to maybe 5 or 4. And the lower it goes, the wider our confidence interval is going to get. So that's our next step. Compute the degrees of freedom. We have the formula above. Let me cite it down below here. The degrees of freedom, we still call DF. But now it looks like this. We take standard error of x bar 1, meant to color code that, minus x bar 2, and we raise that whole thing to power 4. Then the denominator gets interesting, but there's a lot of symmetry in the denominator. If you got one part down, you'll get the other part. And again, this formula would be included on the page of notes if this is on exam 2. If it's on exam 3, it's going to be on the page of notes as well for that exam. But the more you're familiar with this formula, the easier it's going to be to use. So memorizing it is the ultimate form of familiarity. Here's how it goes. It's 1 over sample size 1 minus 1 multiplying sample standard deviation 1 squared divided by sample size 1 to power 2. So that's the first part. Then we add on essentially the same thing, but we're just changing the subscripts. There will be N2 and S2 everywhere. So it's going to be 1 over N2 minus 1 divided by S2 squared over N2 squared. So there's our whole formula. All we have to do is plug in our values we have in this problem. I'm going to go down. So I think I'm going to run out of horizontal space on it. So in this problem, here's our degrees of freedom. First in the numerator, this is again a nice shortcut. Just take whatever value you got for standard error, raise it to the 4th power. 285.4972. Now for 1 over N1 minus 1, that's just going to be 1/5. The sample sizes are balanced, And you might be thinking if the sample sizes are the same, that's the least common denominator here and here. You could actually simplify both of these formulas. I left in this form because our formulas work just fine for unequal sample sizes. So we get 1/5 times S1, here it is, squared, 565.19 to the power 2, divide by N2, back to the sample size 6 on that one, and then raise that to power 2, do it all over again. This will be 1/5, following the format from before on the left. The denominator here is back to 6. Really, the only thing big that's changing, once we wrote it down once, is we're just putting in the other standard deviation, S2. So 411.84 squared goes here, close that off, raise the whole thing to power 2, and this will get us our degrees of freedom. So it's time for the calculator. This is probably going to be the last thing we do for the course. I've just noticed the clock is ticking down pretty quickly. So it's going to be 285.4972 to power 4 divided by, we're going to need an outer parenthesis for that entire denominator. Go 1/5 times 565.19 squared sixths. Close that off. Hang on, my parentheses are not behaving. Okay, close that off. That looks better. Raise it to power 2. Go plus, and that's this first portion right here. Now we're just doing all over again from the second side. The second term, 1/5 times 411.84 squared, divide by 6, raise that to power 2, and close that outer parenthesis. And there's our degrees of freedom. It is 9.1412. Let's call it, 9.1420. Let me double check the rounding. All right, to 4 decimal places, that's our value rounding with carry. That's a pretty intense computation for degrees of freedom. And again, if these sample standard deviations were exactly equal, we'd have some strong evidence that the population standard deviations might have been equal as well, even though that may not be true. But if they were, this would have came out as a 10. The more unequal they get, the smaller this gets, widening our confidence intervals further and further, but making our confidence level we're going for, 95%, being a very, very accurate statement now. So if we use degrees of freedom 10, our confidence interval, it's going to look nicer. It's going to be more narrow, but it's probably no longer at 95% confidence. It's probably dropped down to, say, 93%. Well, we did it, folks. The next step is actually the easiest part of the formulas, just putting it together in the confidence interval. But we'll have to save that when we come back on Monday's class. These were essentially the 2 new elements in dealing with these confidence intervals, the new standard error and the new degrees of freedom. So I'm glad we got through those 2 parts. Any last questions or comments at all, folks, before we call it a day? Okay, well, it's still just Wednesday, but have a great weekend, folks. Hopefully midterms isn't too rough, but we won't be doing anything special in this class. I'm just going to report your grade. The same one you have in Canvas is a letter grade, and that'll be the midterms. But have a great afternoon, folks. We'll be back to it here, seeing what's going on with the rats on Monday's class.